All right, so this is section 1.6. We're going to be doing a review here of complex numbers. And the big thing to remember is that complex numbers can be written in the form a plus bi, where a and b are real numbers and I is, of course, the imaginary number. So I equals the square root of -1. We can't take the square root of a negative number. If we do, we get what's called an imaginary number, or I, something with I. Now, if we square both sides, what we find is that I squared equals, and then if you square the square root of -1, opposite operations there, so we get I squared equals -1. So when we think of the complex number system, it's everything written in the form a plus bi. So you can see that we have the first two examples here that are exactly what we thought. They are a plus bi, they have a real part and they have an imaginary part. And that's why underneath the complex numbers are numbers that are real, numbers that are imaginary. So those make up the complex numbers. Understand that 5i, the third example here, could be written as 0 plus 5i, meaning that its real part is 0 and its an imaginary part is 5i. Even something like 2 could be written as 2 plus 0i. We'd never write that, but it does remind you that 2 is a complex number. It just has no imaginary part. Okay, so our real numbers, so imaginary numbers are, anything with that I. Our real numbers can be broken down even more. So real numbers are take on two forms, either rational or irrational. So irrational numbers are things like pi. So the number pi is irrational. You might think of it as 3.14. It actually goes on forever and ever and ever. And that's by definition an irrational number because the decimal parts also do not repeat. Another example would be something basic like the square root of 3. Because this is not a perfect square, it is an irrational number, meaning that it has this decimal part that goes on forever without repeating. Rational numbers are anything that can be written as a fraction, p over q. So for example, you could have 5 over 3. That's an example of a rational number. You could also have 2, because you can write 2 as 2 over 1. So anything that can be written as a fraction. So notice the next thing underneath rational are your fractions, like we had the 5/3. Integers over here would be like the 2 over 1. So it's broken down into fractions and integers. Underneath integers, you have things like negative integers, so like a -3, a -10. You have, of course, 0. And then you have your natural numbers, which are 1, 2, 3, 4, and so on. Whole numbers are considered 0 and all the natural numbers, whereas the natural numbers don't include 0. But it is good to have an idea. I do use this, this vocabulary. You'll see it in the book. So it's a good idea to be familiar with it. But now we're going to focus just on what we're going to do with these complex numbers, some things we can do with them. Really, the way to think of the I is just that you don't want to think of it as a variable. It's not a variable. It's by definition the square root of -1. However, in order for it to be combined with anything in terms of addition or subtraction, it does need to be a like term. So when we want to add two complex numbers together, we need to add together the real parts and add together the imaginary parts. And so in this case, we'd have 4 plus 2i. We cannot combine it anymore. That is it. We have a complex number here. You can try the same thing with the subtraction if you want to pause and see if you can do the subtraction. No different. You just need to make sure you distribute that minus sign to everything inside the parentheses. And in this case, it looks like we'll have 2 minus 6i. So notice those two values are different, of course, with the addition or the subtraction, even though they're the same thing in the binomial. In terms of multiplication, it's really not anything surprising. It's still the idea of FOIL, or just the idea of multiplying everything in the first binomial times everything in the second. So 3 times 1, and then, and again, welcome to do this on your own. See what you get. Could have moved that down a little bit. The key one is the last one here. So notice when I multiply together the last two terms, I get a minus 2i times a 4i. That's going to be a negative or minus 8i squared. And so what, to remember what I had written up at the top there, we're going to have 3 plus 12i minus 2i, and then that I squared becomes a negative 1 by definition. So we get 3 plus 10i plus 8, or 10i plus 11. I feel like there's a way to like undo, don't you think? But I do not see it. Okay, so here we go. And yes, typically as a complex number it'd be written as 11 plus 10i, just because it's typically real part and then the imaginary part. If you want, why don't you see if you can multiply out the last one? You may notice something interesting. So what we see here is this idea of the conjugates, and it helps us out here. So we find that the middle terms simplify. We get 9 minus 4 times I squared, which is that negative 1. So 9 plus 4 is 13. In this case, it might not seem that exciting, but there is a reason that this is helpful, and we're going to see it now. So I already said, as we saw, conjugates here, a plus bi, a minus bi. And sometimes you'll see this notation here, this line on the top indicates you have a conjugate of something. So we've added, subtracted, multiplied complex numbers, just simple things we can do with them. If you want to divide complex numbers, however, it's just a little bit more to it. This is where the complex conjugate comes in. The idea behind dividing complex numbers is the idea of trying to write this in that form a plus bi. And right now that's not the form it's in. But by using the complex conjugate of the denominator, you can create a denominator that no longer has an imaginary part, which will then allow the imaginary part to stay in the numerator, which will allow you to rewrite it as a plus bi. So we are going to take the denominator and multiply it by 1 minus 4i. Because this is an expression, not an equation, we need to make sure we're doing the same thing to the top, so all we're doing is multiplying by 1. So if you want, you can take a moment or two and see what you get when you multiply this out. Go ahead and pause if you'd like. And notice we have a binomial times a binomial in the numerator and the denominator. Okay. I'm going to do my denominator just a little bit quicker. I know that my middle terms are going to be gone, so I'm only going to end up with this. Because that's the whole point, is that my imaginary part is gone. Then let's see what I'm going to have. So I'm going to have a minus 8 here, because that's negative 1 when I square the I. And it looks like I'll have 3 minus 8, which is a negative 5, and then a minus 14i in the middle. And then our denominator here, yay, is 1 plus 16, or 17. So we're not going to actually leave it like this, because this isn't in the form a plus bi. If I divide, however, both pieces by 17, then it is. So notice now, even though it's fractions, that it is in the form a plus bi, where a is a negative 5/17 and b is a negative 14/17. And then we have our I after that, of course. But both those numbers are real. And so that is the correct answer. And then the last little bit we're going to do with complex, because again, it's not like a huge focus, is to solve a quadratic equation. We've done this. We've done this a lot already. However, you might be not surprised to find out what our answer will be like. If I see this, maybe I'm going to bring over my -7 there. I'm going to add it to both sides. This is not looking like it's going to factor. I'm not going to be able to get that 4 in the middle with the other numbers that I have. I could complete the square. It's possible. It's not going to be as pretty as I would like. So I think I'm going to go with the quadratic formula. So go ahead and do that. If you would like a little bit of practice with the quadratic formula, go ahead and pause and do that. So I'm always going to start with my x equals, because it's telling me here are my solutions. By definition, x is going to equal -4. So 4 plus or minus the square root of b squared minus 4ac all over 2a. Now, you might notice that in the parentheses, we have 16 minus and then 4 times 2 times 7. And you might notice that 4 times 2 times 7 is, it looks like 56. And you might notice that 16 and 50 minus 56 is going to be a negative number. So that's kind of the key thing to see here. So I'll do one more line down here. This will give us 4 plus or minus the square root of -40 over 4. I still can't do any simplifying left yet until I have simplified that square root of -40. So I'm going to bring it up here and get x equals 4 plus or minus. And then we really just want to remember that when we think about 40, that's 1 times 40, 2 times 20, 3 times, nope, 3 times nothing. 4 times 10. What I'm doing here is I could take this into, prime factors, but I'm just thinking about, is there any of those really common perfect squares? And we can see that 4 times 10 gives us a perfect square with the 4. So what this means is, let's see how many steps I want to do here because I can't cover my face up. So what I want to understand is I'm going to take the square root of a -4, and then I'm going to leave my 10 inside because it is not a perfect square. Then I'm going to take the square root of that -4 to give me 2i square root of 10. And now I should see that I can simplify a factor of 2 here, here, and here. And now I can just have the most simplified version of my answer. So x equals 2 plus or minus I root 10 over 2. And then I can very easily put that into my solution set to say here are the 2 solutions. They do in fact make this equation true. That is the key to understand. I can't do any more simplifying there, but they do make the equation true. If you were to plug them back in for x, again there's 2 solutions there because of the positive and the negative, the plus and the minus. You plug them in and you actually are going to get both sides being equal. It just happens that the solutions are imaginary. And I've mentioned this before, but if we were to consider the function f of x equals 2x squared minus 4x plus 7, if we were to graph that, what we are going to find is that it would look, that was not as pretty as I wanted it to be, it is going to look something like this. So the key thing to see here with this is it's just a sketch, but if we were to graph this function, it would sit above the x-axis. There would be no place where it crosses the x-axis. That is because of the relationship between the equation we found and what that function would look like graphically, and where it would be equal to 0, which is the idea of crossing the x-axis and being x-intercepts. This does not have any, And so that's why we get the imaginary numbers when we solve that equation. That's section 1.6.